specific latent heat. Is that okay? I mean, sometimes we don't put specific for latent heat. We could just say latent heat. The same. So, and specific latent heat. SHC and SHL. SLH. All right, now we said that. Now listen, I'm going to explain first before we take the notes. I said that we've said before that temperature and heat are not the same, right? Temperature is not heat. It's not heat. Does that make sense? So it means that because, of course, we know that heat is an energy, it's a form of energy, while temperature is just a measure of what? Hotness or coldness. But actually, on the molecular scale, we said that temperature is the measure of the kinetic energy that a system has. Is that okay? So that kinetic energy is internal. We call it internal energy. You understand? So the measure of the internal energy that the body has, but we perceive that measure of internal energy as temperature, just as coldness or hotness. Does that make sense? You perceive that internal energy as what? Coldness or hotness. Now, so what is energy? Or what is heat energy? Heat energy is basically what causes temperature, right? What causes rise in temperature or fall in temperature. So it means that if I add heat to something, that thing should what? Increase in temperature. If I remove heat from something, what should happen to that body? It should reduce in temperature. All right, so it means that heat is basically the amount of heat that I need to add to something to increase the temperature by 1 unit, say 1 degree Celsius, say 1 degree Kelvin. Do you understand now? So that is what heat is. Now, let's explain what specific heat capacity. No, let's start from heat capacity, right? So we say heat capacity is what? Exactly. Heat capacity is quantity of heat required. Now it is denoted by C. I got corrected recently. It is denoted by C. Is that okay? But heat energy is represented usually in A level, like Q. Yeah, when you be doing your first degree, so it's Q. You mostly see, even in chemistry too. Remember? Alright, because we reserve H that you might be expecting. Reserve it for which quantity? Enthalpy. Change in enthalpy and all. Enthalpy in chemistry. Alright. So we said heat capacity is the amount of heat that is required to cause the temperature of the body to increase by one unit. And it is mathematically described as the product of mass of that body that wants to increase the temperature times the specific heat capacity of that body. Now, what do we mean by specific heat capacity? We are going to get the definition soon, but let me explain what that is. Now, you will discover that if you are boiling water, which one gets hot first? Is it the pot or the water? The pot, right? Now, was it the other day we were doing it? We discovered that copper, let's say your pot was made of copper. Copper had this specific heat capacity of 390, right? Approximately 390. While water has specific capacity of 4,200, isn't it? Now, let me explain what this means. The reason why when you boil water, the pot heats up first is because the pot is a metal. All metals have higher, most metals, not all. Is that okay? Most metals have higher specific heat capacity than water. So because of that, what that specific capacity means is that the amount of energy, heat energy, that is needed to be imputed into that body before it rises in temperature. So for example, the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. What this means is that you need to put in as much as 4,200 joules of energy into that water Do you understand? For that water to increase in temperature by 1 unit. Does that make sense to you? Unlike copper, that pots the pot. But the moment you begin to heat it up, it begins to rise in temperature. In fact, you notice that if it's a good enough, if it's a good pot, that this thing, at the moment you put it on fire, it will start to heat up, and you're just pouring water inside, or the water that is inside has not even started to gain heat at all, and has not changed temperature at all. Do you understand? So that's because the copper needs only little amount of energy to what? Increase in temperature. And the reason is because, think of it as the fact that it already has a higher internal energy. So you don't need too much energy again to cause what? An increase in temperature. Does that make sense? Is it clear? All right. So now let's talk about. So now, right now, this one is measured in. What do you think will be the unit of measurement of this? Let's talk about the specific heat capacity first. We'll come back to the measurement, the unit of this specific heat capacity, right? SHC. This is defined as the quantity of heat required. The quantity of heat required to raise a unit mass of a body. SHC is the quantity of heat required. The quantity of heat required to raise a unit mass of a substance. A unit mass of a substance by 1 Kelvin or 1 degree Celsius. To raise the temperature of a body, to raise the temperature of the unit mass of a body. To raise the temperature of a unit mass, not just to raise a unit mass. To raise the temperature of a unit mass of a body by 1 Kelvin or 1 degree Celsius. All right, and we said that SHC is denoted by small c. So there's big C and there's small c. Big C is heat capacity, or what's we call it thermal capacity. I mean, the word thermal refers to heat already, right? So thermal capacity is heat capacity. So it's denoted by big C. Specific capacity is denoted by small c. All right. We said that one is the what? That small c is the what? Quantity of heat required. Yes, God bless you. So what that means is that mathematically we define it to be the specific capacity is the quantity of heat per unit mass per unit rise in temperature. Does that make sense? Does that make sense to us? Specific heat capacity, SHC, will be the quantity of heat that you used per unit mass per unit rise in temperature. Unit rise in temperature means change in theta, that's delta theta. Is that okay? All right. So what do we make of Q now? So Q will be the what? Total heat energy. Total what? Heat energy is going to be equal to, from here, what do? You cross multiply and you have what? Q equal to MC delta theta. Does that make sense? Okay, so more expansively it means MC into bracket theta 2 minus theta 1. What is that? Do you get this? Is this clear to you? What is not clear? This part. We just cross multiply. So it will be C times this and Q times 1 is equal to Q equal to M times C, MC. Do you get it now? So do you see that there is similarity here? This one is MC, this one is MC. So it means that we can say that Q is also what? C delta theta. Does that make sense? All right. So that's the specific. Heat energy, total energy is equal to or quantity of heat is equal to heat capacity times change in temperature of the body. Is that okay? Heat capacity times change in temperature of the body. Now let's analyze the unit of this guy now. What's the unit of heat energy? Joules. The unit of all energy is joules, right? So what will be the unit of specific heat? the unit of mass rather, kilogram. The unit of change in temperature, Kelvin, right? That's our unit of measurement of temperature. All right. So this becomes joules per kilogram per Kelvin, or you write it as joules per kilogram per Kelvin. Is that okay? All right. So bringing that onto this place, we can now make sense of this. Heat capacity will now be what? That will be kg, unit of heat energy now, kg, which is for mass, times C. C is joules per kilogram per Kelvin, right? So kilogram cancel kilogram, then C is equal to what? Joules per Kelvin, or joules per degree Celsius. Is that okay? All right. I told you why it is the same for Kelvin and this thing, Kelvin and degree Celsius, because you don't need conversion. Because if you converted, you know that I told you that Kelvin 273 will cancel out. So that is why it's the same as joules per degree Celsius. Have you put that down? All right, put it down. And let's go to solving a question. Okay. Yeah, let's go to solving a question. The different forms of the formula I'm going to give you. Different forms of the formula. So the first form that you might see is this one. That Q is equal to mc delta theta. But we know that energy comes in different forms, right? All right. So now the different forms of the formula are this. Now the first thing you should know is how did they find out that the specific capacity of water, for example, is 4,200? How? Or for any substance, or for any substance. So let me use the electrical method. So I mean that will bring us to calorimetry and the likes. All right, but now this is it. If I have a bowl containing water here, now containing water, and I needed to calculate the specific capacity of this water, I know the mass of this water, right? By measuring. Now. But if you don't even know the mass of the water, another way you can use to measure the mass of the water is by taking density is equal to mass over volume. Density of water, provided your water is pure, is about 1,000. That is 998, right? Density of ice is 917, right? Yeah, because I was explaining to someone recently and I said one of the reasons why ice can also float on water is because it's less dense than water. That's why it's on top. Although I've explained the fact that anomalous expansion of water, do you remember? And that so that ice is that ice has a higher volume than water. So because of that, it has lower density. I mean, of course, this is density. Okay, now let's go. So we know that it's about 1,000. Then you know the volume of the water by calculating the volume of the container. You can get the mass of the water. Does that make sense? All right. So if you insert a water heater inside, we did this in class also. So you insert a water heater. The water heater will be plugged to a circuit. I mean, so you plug it. Doesn't look like your this thing. So you plug it to a socket. By the time you plug it to a socket, current is going to be passed into this and it will generate heat here. Is that okay? It has an electrode that heats up. Is that okay? This metal is an electrode that heats up when current is passed through it. Is that okay? It works like a resistor. Do you get it? Now it heats up, and as it's heating up, like this, it's generating some heat into this guy, right? We do know how do we calculate heat energy? Energy loss. When we did electricity, in current electricity, energy dissipation or energy usage. Now we said that power is equal to current times voltage. Do you remember? Do you remember this? Okay. Power is current times voltage. Now why did I introduce power? Because the only equation that brings energy and that we can use to relate power and energy is this. That work done is equal to Power is the rate at which work done is done. Do you remember that? Power is work done over time. Do you remember this one? And work done is the same as energy, isn't it? I mean, of course, energy is required to do work, but in this case, we know that by formula they are the same. mgh here, work done, force times distance, here, mgh, right? So mgh per t. So here, electrical energy is what we need. Energy, the formula has not changed, it's just that the form has changed, right? So energy here is going to be what? So in this case from here, energy is going to be what? Power times time. Does that make sense? Is it clear first? All right. So we know this. So in electricity, we know that power is current times voltage. All right. So if this is the case, then also we know that E can therefore be equal to power, which is IV, that is IVT. Does that make sense? Okay. So this time we'll be talking about electrical energy being converted to heat energy. That makes sense, right? Electrical energy from this source will be converted to heat energy here by the electrode, right? But since there is conservation of energy, no energy will be lost. So the total, so assumably, we can say that the total electrical energy is converted to what? Heat energy here. Is that okay? Good. So here, the formula can also change. Remembering that, do you remember this color formula triangle? V equal to I, R. Formula triangle. V is equal to I. So I will be equal to what? V over R. So this will be equal to I, which is V over R times V times T. So electrical energy is also equal to what? V squared over R T. Does this make sense? Another is I will be equal to V over I. That R will be equal to V over I. That's the essence of this formula triangle. You can make it, you can use any formula to make it. You can use force equal to MA, and so on and so forth. So, but the point is this. The point is this. E will be equal to what? If R is equal to V over I, and R is here. So we have that V squared over R is now what? V over I, right? That will be V over I. I will come up. Does that make sense? N times T. So that E will be equal to what? V takes care of 1V. Okay, IVT again. I think of V. Okay. You get IVT again. I wanted to make V. V is IR. So let's change this. So V will become what? I dot IR dot T. Does this make sense? So E is also equal to what? I squared RT. These are different forms of the formulas. We have equation 1, equation 2, equation 3. Is that okay? All right. Now, so the amount of energy here is the amount of heat energy that we supply there. And we know that total heat energy is equal to what? MC changing theta, right? Okay, so by bringing all the formulas together, heat energy here will be equal to electrical energy by principle of conservation of energy, all right? So when we bring that in, it means that our energy, either we use V squared, let me bring it here. We said Q is MC changing theta, but Q now has become the electrical energy. So electrical energy is V squared T over R is equal to MC delta theta. We started off from here to IVT rather is equal to what? MC delta theta. IV is power. PT is equal to what? MC delta theta. You are not getting it, raise your hand. You are getting it, right? Then the last one there, I squared RT. I squared RT is equal to what? MC delta theta. And this is all the possible formula combinations that you can have. Does that make sense? So this is one of the ways by which the specific capacity of water was measured. Because knowing the electrical energy that will give us this, so I know that IVT is equal to MC delta theta. Now I'm looking for the specific capacity of that. We already know the mass by this calculation, right? And we can put a thermometer here to measure the temperature. So by measuring the temperature, we'll know the change in the temperature, right? At the beginning and at the end. So with that, and you know the amount of current that is flowing and the time over which it flows, you get the energy, and with that, you are able to do what? Calculate the C. Does that make sense? Is it clear? All right. Now, what if we were talking about mechanical energy? Mechanical energy, that is work done, mechanical work done. Okay, let me leave here so that. What if the work done was mechanical? So, for example, where a body is moving speedily, and if the body was moving speedily, for example, I talked about a waterfall, right? Waterfall, for example. Now, the temperature of that water as it drops at the top is slightly different from the temperature at the bottom. So it's because of when it was at the top, it has what kind of energy? Potential energy. We said potential energy is the energy a body has by virtue of its position above the ground. Is that okay? So when it is high on top there, it has potential energy. By the time it's coming down, it will have a slight increase in temperature because it has converted potential energy into what? Heat energy. Good. So potential energy is equal to mgh, right? But we recall that heat energy is also mc change in theta. At the base of the distance, all potential energy would have become what? Heat energy. Is this clear? Raise your hand. So we have mgh will be equal to what? Mc delta theta. So what you will soon notice is that if we are talking about the same body, then m can cancel out. Does that make sense? So what affects this thing, basically, the only factor that affects changing temperature for a body like that is, let's see, this is what we're left with, right? The only factor that affects it is the height over which it falls. So if it falls from a higher height, it will have a higher temperature. A lower height, a lower temperature. Does that make sense? This formula also holds true because we know that G is constant, right? So H equal to C delta theta over G. Okay. Another formula is if it was moving, at the point where it's on here, that water too, at the point where it's moving, you know that if water is dropping, if something was dropping from the top like this, it was dropping. At this point, when it was stationary, all energy was what? Potential. Does that make sense? By the time it gets to the bottom here, all energy, just before it hits the ground, all energy will what? Kinetic. But when it touches the ground or rests at the ground, no energy, right? Zero. So now, I wanted to say something. Now, so it means that from here, kinetic potential energy was the only energy. Kinetic energy was zero when it was not moving. At the moment it began to move, potential energy began to reduce, while kinetic energy began to increase. We know that, right? Because as the body falls like that, what happens to the velocity? It increases, right? Are you getting it? Acceleration is still acceleration due to gravity, but there will be uniform, there will be increase in velocity. Now, as the velocity is increasing like that, so it shows that the velocity with which it falls is going to be the major determinant. So that's what I want to say. So at each point here, it possesses kinetic energy, which is half mv squared. So if no energy is lost too, the total kinetic energy at that particular point will be converted to heat energy. So we can also see that half mv squared is equal to what? Mc delta theta. Does this make sense to us too? So m can also cancel m. So what is the major factor affecting change in heat here? Velocity. The speed. So if it falls at a higher speed, it's going to have what? A higher heat energy or change in temperature. Does that make sense? Alright, those are the possible combinations of formula that I can have for specific heat or for specific heat. Alright, now let's talk about calorimetry. That's another form in which the formula can exist. So by calorimetry, we mean there is a this is the layman explanation of it. Now there is a container, there is something that has an amount of heat, and there's another thing that has a lower amount of it, maybe, and you want heat to move from one of that medium to the other. An example is when your food is hot, or when your tea, for example, is hot, what do? You pour water into a bowl, right? So you pour water into this bowl, and you now put your cup inside, right? Isn't it? So your tea is hot, you want it to cool faster. So this system is a calorimeter. Does that make sense? So what it does is this. I mean, this is the way the calorimetry system is too. So what it does is this. There will be heat transfer from here to here. So this system will do what? Will lose heat. We experience heat loss. Why this system here? Water here, we experience what? So keeping in mind that in an isolated system, no heat will be lost, right? So we always say that heat loss, no energy is lost, rather, conservation of energy. So heat loss will be equal to what? Heat gain. So we definitely mean H of 1, that is, I mean Q rather, Q, let's use Q rather. So Q will be MCQ changes theta here. So here we have MC delta theta here will be equal to MC delta theta here. Is that okay? But here we will know that there is heat loss, right? So sometimes by sign convention, you even have a negative here. But since it's a change in temperature, you can decide to flip. Oh, is that okay? But a change in temperature here that I mean now is that there is what? Reduction in heat. Is that okay? Yeah, I told you that negative will be a property. What's the property? Reduction in heat. Is that okay? Because it's losing heat. But if you decide to arrange the temperature correctly, put the higher one before the lower one. That is, in this case, MC theta 2 minus theta 1. So if this body is losing heat, the theta 2 should be what? Less than theta 1. Do you understand? So this tea, maybe you boil this tea to be at 80 degrees Celsius. Is that okay? And by the end of the reaction, you want to be able to drink it at 40 degrees Celsius. So what is the heat change here? So we have MC. What's the second temperature here? 40 minus initial temperature 80. So this is going to be negative 40. So the negative that is ascribed on this guy is to show that heat has been lost. You could decide to use 80 minus 40 so that your answer will be positive if it confuses you. Because if you put that, in some cases, you will have to still reintroduce that negative. All right. So my point is this, that in this one, there will be heat gain. So if the water was at 20 degrees Celsius before, it will increase by the same amount of temperature that was lost here. Is that okay? So which will be here, theta 2 will be less, theta 2 will be more than theta 1. So what's the amount of heat that will be lost here? 40, right? So this one will also gain that 40. That will be MC this time. 40. No, if it gains, it was at 20 degrees Celsius, if it gains 40, that was 60 minus 20. Does that make sense to us? All right. So here will be positive, here will be negative. So the side that is positive is the side that gain it, the side that is negative is the side that lose it. Is that okay? All right, let's see one question. Right. What is the quantity of heat? What is the quantity of heat that will be given out? What is the quantity of heat that will be given out if a bar of brass of mass 350 grams 350 grams is cooled from 95 degrees Celsius 95 degrees Celsius to 20 degrees Celsius. SHC of brass is 380 joules per kilogram per Kelvin. Okay, so let me solve this very hard one so that you will solve simple ones. Is that okay? You know it's hard, and I don't want hard things for you. Is that okay? You know it's low. Yeah, I don't want you to be doing hard work. So let me do this very hard one. You now do the very simple one. Tell your neighbor, very simple one. All right, let's go. Now, we could draw diagrams. Is that okay to help ourselves? You know, let's just say this. When we're doing waves, I told you about the reason why you can use, reason why you should try to draw diagrams when we're doing front of camera, front of mirror, back of mirror, and those things. So using diagrams can be of good use for you. Is that okay? What is the quantity of heat that will be given out if a bar of brass of mass that? So this is the mass of brass. Is cooled from that. Okay. We don't really need more diagram here. It was cooled from 95 degrees Celsius. The mass of this thing is 350 grams. So we have to change to what? Convert to what? Kilograms, right? So how do you convert from to kilograms? This will be equal to 1 kilogram, times 1 kilogram over 1,000 grams, right? So gram cancel gram, divide by that. That's just unit of conversion. All right, so what you just do is divide by 1,000. What would that give you? 0.35 kilograms. All right, so now it says, what is the heat given out? Heat given out, we are not concerned where it's going to. Is that okay? We are giving C also, specific heat capacity. C is what? 380 joules per kilogram per Kelvin. We are giving change in theta. What will change in theta be here? Theta 2 minus theta 1. What was theta 2 here? 20. What's theta 1? 95. Now, so this is where, since we are not concerned about where the heat is going to, we can switch it. Is that okay? Because here it will give us a negative 75, right? Negative only tells us that what is happening. Heat is being lost. Is that okay? So the arrangement is not really necessary. It's not really of great importance. It doesn't affect our formula, that is. So MC change in theta. So we have Q will be equal to what? M, which is now 0.35 times 380 times 75. Does that make sense? Then Q will be equal to what? 9,975 quantity of heat joules. Is that clear? All right. Now, copy that and I'll write some questions on the board. You will now begin to solve. You see how? All right. So the question says that how much heat energy will be needed? I don't need to finish reading the question. I go on to writing my parameters first. See, that's the way to do it. You write your parameters first, the things you are given, knowing the formula. Is that okay? So you say how much heat is required. How much heat? That's what we're looking for. We're looking for how much heat. Heat is key. Is that okay? To change the temperature of this amount. This is mass, right? Gram. So we have mass is equal to 275 grams. But we need our guy in kilograms. So we divide by 1,000 grams. Is that okay? So that becomes what? 0.275 kilograms. Does that make sense? So then it now says change the temperature of this amount of mass of paraffin oil by, what's paraffin? Okay, do you remember? Of paraffin oil by 75 kilograms. 75 Kelvin. To change it by, when you hear by, that's the change in temperature. It's not to change it to 75 from this. Do you understand? By means that is the rise in temperature or change in temperature. Is that okay? So you have change in temperature, delta theta is equal to what? 75 Kelvin. You don't need to convert here to degrees Celsius. All right. So SHC of paraffin, that's small c. That's what we use to represent SHC. SHC is specific heat capacity of paraffin. We use small c to represent it. It's equal to 2130 joules per kilogram per Kelvin. And you can decide to write that. Joules per kilogram per Kelvin. Now, How do you now apply a formula? You now recall your formula. That you remember that your formula is Q equal to MC delta theta. Do you remember this? So this formula, is that okay? See, this formula for heat energy. This is the formula for heat energy. So we now say that Q will be equal to now, M is this guy, 0.275 times small c is this guy, 2130 times change in theta is what? 75. Then you multiply through. And what do you have? 43931.25 joules. Because heat energy is in joules, right? All right. Okay. Let's go on. Number 2. Number 2 says, calculate the final temperature. So what's final temperature? Theta 2. Remember that change in temperature means, are you there? If I say delta theta, delta means change, right? It means there is a change in temperature. So if I want to calculate change in something, if I want to calculate the change in your height, I will measure your new height from your former height, right? So that is our new temperature minus our old temperature. We use theta to represent temperature. Is that okay? So what we are looking for here is theta 2 because it says calculate the final temperature. That's theta 2. We don't know theta 2. So it means we must have been given theta. All right. So what's theta 1 here? 25 degrees Celsius. You simply getting it. Look at it here. But let's read through before we start jumping. All right. Calculate the final temperature of that mass. So the mass is what? 2 kg. Is that clear? Of alcohol at 25 degrees Celsius. So the initial or the first temperature is 25 degrees Celsius. When 2016 joules of energy, does that make sense now? Of heat energy. So Q is already given 0.20160. Is that okay, Simbi? Of heat energy is added to it. Are you getting it? All right. So we've added that amount of energy. We want to know what the new temperature will be. So given all of this, let's see. We have Q is MC change in theta. All you need to do is, after you have mastered this formula, just come and check which one are you not given. We've been given, if we expand it, it will become Q equal to MC into bracket theta 2 minus theta 1, right? Okay. So M is given, M. C small c is given. Small c is given, right? Yeah. So small c is what? 2520 joules per kilogram per Kelvin. Is that okay? So this guy is given. Theta 2 is not given, but theta 1 is given. So that's what we're looking for. So Q is this, right? So we say 20160 is equal to M is 2. 2 times Q is, C, small c, is 2520 into bracket theta 2 is what we're looking for. So we leave that as theta 2 minus theta 1, 25 degrees Celsius. All right. So we now have 20160 is equal to 2 times of this, 5, 2 times is 5, that's 5 now, 5040, right? Into bracket theta 2 minus 25 degrees, right? Just use 25 minus 25. So you can now begin to solve maths, basic maths. 20, we can cut the 0 out since, or would that confuse us? If it will confuse you, you can just solve directly, but I just want it to be simpler for me. 2016 is equal to 504 into bracket theta 2 minus 25. So here we have 2016 is equal to this times this, 504 theta 2 minus 504 times 25. What? 126,000. No. Check again. 12,000, yes, half. That's 12,000, that's correct. So what do you now do now? You collect like terms, right? So this guy will come here. So we have 2016 plus 12600 is equal to, you simply getting it. 504 times 25. So we have this plus this. 14616. That's all. Is equal to, yes, 504 theta 2. Divide both sides by 504. And you have 7, right? 21. 29. And 29. That's all. Oh yeah. 29 degrees Celsius. So that is what? Theta 2. Is it simple, right? Okay. Now let me solve number 3. Did number 3 give you a problem? No. Charles, did he give you a problem? What's your answer? What's yes? Did he give you a problem? Okay. What did you get number 1 and 2? Did you get it so far? Okay. Now number 3. I don't like things like this. Now it's like it's one big thing you've done. You can do this in 2 lines. But let's just go. I'm expatiating because of you guys. Is that okay? So make sure you are getting it. Now number 3. When 100 grams of liquid, don't finish everything, just go there. 100 grams of a liquid, so M sub L of liquid L1. So M sub L1. Is that okay? That's mass of liquid L1. That's what I mean by M sub L. So M sub L1 is 100 grams. So what would that be in kg? 0.1 kg. Is that clear? At 78 degrees Celsius. So its initial temperature is what? 78 degrees Celsius. Does that make sense? Banana did what? Was mixed with X gram of liquid. So now in mixtures, to be like that calorimetry formula too. The one will lose heat, the other will gain heat. So was mixed with X gram. So M sub L of liquid L2, M sub L2 is X gram. Does that make sense? How do you convert this? You see divided by 1000, right? So this will be X over 1000. Is that okay? Who is lost? Good. This one, its own temperature is 50 degrees Celsius. Theta, so this one is theta 1 of L1. So what do we do? Theta 1 of L1. Theta 1 of L2. Is that okay? This is the initial temperature of this guy. So what is that? That's 50 degrees. So where will heat flow from? Is it from M1 to M2 or from M2 to M1? Do you understand? Where will heat flow from between these two? Is it the guy that has this temperature or the guy that has this temperature? Will heat flow from this guy to this guy or from this guy to this guy? You don't understand? Which one is hotter between this guy and this guy? Okay, that one is hotter, right? So where should heat flow from? Should heat flow from the hotter one to the colder one, or from the cold one to the hotter one? Yes, the hot one to the colder one. So this one is colder. I mean, it's not cold. 50 degrees is not cold, but this one is hotter, right? So this guy will heat will flow from the hotter one to the hot one. Does that make sense now? All right. The final temperature was 66 granotes. So it means that both of them attain equilibrium temperature. Theta 2, 66 granotes. Theta 2, also what? 66 granotes. Granote Celsius, degree Celsius. Given the SHC of L2 is half that of L1. So SHC of this guy, L2, is equal to 1 over 2C. So let's say, wait, listen now. Let's say SHC of this guy, small c, is C. SHC of L1, let's call it C. SHC of L2, C of L2, it will be half of that guy. Are you lost? Is Simbi lost? That's what it says. There is half of that. So let's say we call the SHC. SHC is always represented by small c, right? Is it? Okay. So we know that SHC is always represented by C. So we now call that of L1. Let's call it C. But that of L2 is half of that of L1. So that will be half of C. Does that make sense? Then we'll now have, so we have all of this. So what do we calculate? How do we calculate? We know that when we heat, we lose heat to the other because they attain an equilibrium temperature. So we have heat lost is equal to what? Heat gained. So who will lose heat? This guy, right? So heat is, recall that heat is MC delta theta is equal to MC delta theta. That's what we're trying to do. But these MC delta theta are for different guys. So it will now be M sub L1 times C. The C is C. I was going to, hey, welcome. I was going to pick it up. No. I actually wanted to pick it. You said I was going to post it. I know what it's calling me from. It's calling me for, right? Are we there? So we said that what? What did we say? So S C for 1, we made it C, right? Are you with me? Then change in theta. What is the change in theta? That's theta 2 minus theta 1, right? In this case, it will be lost. So we could decide to make it positive, change in theta. So that will be 78 minus 66. Is that okay? Is equal to M. Okay, M of the other guy is X, right? X grams times the C of this guy now. Are you getting the guy that gained heat? Its own C is now half of that guy. So that is C over 2 times. Does that make sense? Let's use dots. It's looking at plenty x's. Plenty x. Then times change in theta. So what's the change in theta here? You have 66 degree from 50. So that's 66 granules minus 50 granules. So here what do we have? M sub L1 times, okay, you notice that C can cancel out, right? C can cancel C here. Is that okay? So by the time, what we're going to be left with is this. M sub L1 times this minus this will what? 12, right? Times 12 is equal to X over 2 times 16, right? So by the time we cross multiply, we have that 2 times this, when you cross multiply, 2 times M, that's 2M times 12, 24M. 24M sub L1, does that make sense? Is equal to 16x. Are we giving M1? Ha. So M sub L1, so that'll be 24 times M sub L1 is 0.1 is equal to 16x. So okay, yeah, that's true. Our x is x over 1000. It doesn't change anything. You know what we'll do? Let's just turn this back to 100. Is that okay? Since we use x directly here. Is that clear? Are you sure it's clear? Is it clear? If I wanted to use this 0.1, I'll just come and divide this by 1000. I'll just put 1000 here. Is that okay? Let's change it back to 100. Do you know why we are changing back to 100? The options are given in grams. So since the options are given in grams, it's not compulsory to convert again. All right. Because when you convert, you still have to convert back to grams. All right, let's go. So this guy, we'll cancel this guy. 8 here, 3, 8 here, 2, here 1, here 50. So x is equal to what? 150 grams. Is it clear? All right. Now, before we solve more questions, let me quickly explain what latent heat is. Latent heat, right? Latent heat. We still have many questions on that specific. So, you know those formulas I gave you are for the different types of different type of question. You talk about a body that is falling from this thing, you use P equal to what? MC whatever. If you talk about heating, an electric heater, the power rating of that heater, right? PT equal to that, or IVT and all. Is that okay? All right. Latent heat. Now, if I say something is latent, what does it mean? I like that. I say something is latent. What did you say? Lead to, okay. Latent, lead to. LL. Did you see that somewhere or you just guessed? Who can give me another? What is latent? I say is a latent. In my course, there's something we call latency period. And if you want to breed fish, they usually inject it with something, you know, right? Okay, you don't know. Okay, don't worry. There's also something called latency period in many things, in many different things. For example, if you want to hatch a species of fungi, that has, you want to hatch it, yeast, for example, you want to hatch yeast. Okay, good. Your mom prepares cake, right? Right after making the dough, there's a time she covers it for the dough to do what? To rise. It's the yeast that is rising there. Does that make sense? So that period when you leave the dough to rise is called latency period. It's called what? It's like period of very subtle effect of anything. So the word latent actually means hidden. The most or the closest synonym is hidden or unknown or not really felt. Do you understand? All right, so the latent, okay, now the latent heat is defined. Latent heat is defined as the amount of heat energy. It's also called specific latent heat. So whether it's SLH or LH, it's the same. Latent heat is described as the amount of heat energy needed to. Latent heat is the amount of heat energy needed for a change of state to happen. Needed for what? A change of state to happen in a substance. There are two forms of latent heat. We have the specific latent heat of fusion of ice. Is that okay? And that's melting. Now it usually confuses students when you hear of fusion and then they say it's for melting. Because fusion, what does fuse mean? To come together, right? I'll tell you why it's called fusion. Then we have specific latent heat of what? Vaporization. That is to what? To boil and form what? Vapors. Is that okay? To form steam. Oh no, we'll not use steam because steam still has water molecules. You understand? Steam has water molecules. Alright. So now, specific SLH of fusion, write that. SLH of fusion Oh, I didn't put something in that definition of latency. I said is the what? To happen in a substance without change in temperature. Without a change in temperature. So in the formula, because in the formula you will not see change in theta. Alright, right now. So SLH of fusion of ice into bracket melting is the quantity of heat required to melt a unit mass of ice. SHC of ice into bracket melting. Put it at melting there. the melting of ice is the amount of heat required to melt a unit mass of ice, a unit mass of ice. Say 1 kilogram of ice, for example. If you're using, if our unit is kilogram, if our unit is gram, say 1 gram of ice. So it's the amount of heat required to what? Melt a unit mass of ice. ICE. To melt a unit mass of ice without a change in temperature. It's simply lost. Latent heat is the amount, SHL of ice is the amount of heat required to melt a unit mass. To melt a unit mass of ice without a change in temperature. While SLH of vaporization is the amount of heat required, SLH of vapor is the amount of heat required to vaporize a substance. The amount of heat required to vaporize a unit mass of a substance, to vaporize a unit mass. It's always 1 unit mass. It's a measure of unit mass. Is that okay? To vaporize a unit mass of a substance. So when we say vaporize, what does that mean? To make it turn from what? Liquid to gas. All right. So it's still change of state. If you follow the first definition I gave, is that okay? So to what? Vaporize a unit mass of a substance without a change in temperature. All right. Let me show you graphically how that is, achieved. So now this was the way the experiment was performed. So water, for example, will be, we boil water. So if I put in my pot of fire, if I put ice, for example, inside like this, my ice is just standing there. The moment I begin to heat it with fire, you are going to notice a rise in, this is temperature against maybe time, or against the amount of energy. Is that okay? Could be against the amount of energy, could be against time. But the idea is that energy is rising. Energy will be increasing, or the time is increasing as which you are heating. But temperature does not always increase. What do you expect the more you add heat to this thing? What should happen? A rise in temperature, right? A linear rise in temperature, right? But that is not what was noticed. That's not what was noticed. What was noticed is that substances first require some heat, some energy. So they will gain that amount of energy. Please focus on the board now. They will gain that amount of energy to a point for water, for example, to gain that amount of heat to 0 degrees Celsius. I mean, it doesn't really start at 0. When you put fire, fire does not start at 0 degrees Celsius. You understand what I'm saying? But let's assume that the amount of heat before supplied is that 0 degrees Celsius. Now, to get it to 0 degrees Celsius. So when water gets to 0 degrees Celsius, what does it begin to melt, right? So it will melt for a while. So some energy is still going into. So let's say it was against energy. So let's say we're graphing against energy. Some energy is still going into it, right? But at this point, this was the point where it stopped to what? To rise in temperature. Does that make sense? So let me tell you what that energy is for. Now, when this amount of heat got into it, it increased the kinetic energy of so if it was ice, of the molecules of water. Is that okay? So the more heat you now, by the time it got to 0 degrees Celsius, everybody has become energized to 0 degrees Celsius. The more energy you now supply now is used to break the bonds. Now, the reason why it's called fusion is that I'm going to show you another graph that shows the regression of that thing. That's why it's named fusion of ice. So this guy is going to require some energy to first break the bonds. After the bonds have been broken, everybody is now set loose. We are no longer together here. We are now liquid. Does that make sense to you? So it means that latent heat is the amount of, so this heat here, is there a rise in temperature? So the heat here is what you call latent heat. The heat that was used up here is what you call what? Latent heat. Hidden heat, because it doesn't look like heat is supplied here, but energy is still being supplied because at that point there is no change in temperature. Is that clear? Good. Now, after this thing has now become water, our guy has now become water. The temperature of water is now at 0 degree and it needs to begin to increase. So you now increase the kinetic energy. Everybody now start running again, convection and all of that to start taking place. So then the temperature will increase all the way to, how many degrees will it begin to boil? 100 degrees Granite. Do you understand? Degrees Granite. Granite or degrees. Alright, so at 100 degrees Celsius, this thing will now begin to boil. So it is at this point, some energy is also required to break the bonds so that every molecule fly off on its own as gas. So then there is latency again. There's latency. So that is, there's still energy you've not removed that thing from fire. You've not. But some of these molecules have decided to what? Escape as gas, right? So as they have begun to vaporize, so here vaporization occurs. Here what happens? Melting. Is that okay? So the quantity of heat that is still supplied further, but did not lead to an increase in temperature, but led to the breakage of bonds, is what you call latent heat. So if you hear what amount of the quantity of heat that is required to break bond within water molecule is called what? Latent heat, not the specific heat capacity. Specific heat capacity of water will do what? Will increase the temperature of water. Do you understand? So it means that all of this place, what do we study here? SHC. Do you understand? All the heat that has anything to do with this place is what? SHC. But this place, what heat? Latent heat. This place, what heat? What about this place? So if it was possible to still increase the temperature, I can still continue to increase the temperature. Do you get it? But at that point, there's no other thing that's happening to water again. It has become gas. Is that okay? The other stage of matter after gas is what? To come back to how many states of matter did I teach you? 4, solid, then to increase in kinetic energy become liquid. So here to solid, ice, here liquid. So by the time it turns here gas. So after gaseous state, what's the possible state of energy? Positive. Plasma. So let's see if you told you. Holy Spirit. Plasma. No. I don't know if water changes to plasma. In fact, I doubt it changes to plasma. But I told you that difference in this gas, it still looks like gas. Is that okay? But the difference is that degree of randomness is higher. That is, kinetic energy is higher. But also the fact that gases cannot conduct electricity. Gases, no gas can conduct. So if you see which of these can conduct electricity, N2, O2, any of the gases mentioned, they cannot conduct electricity. Is that okay? So, but plasma state of matter can conduct electricity because it will be ionized in that state. But don't worry about that. So that's not what we're focusing on. So this is it. Now, so the reason why this guy is named so thing of fusion is this. If we regress this graph, what does it become? In the regression graph, we'll see that we're coming at it from a high temperature gas, right? Right? We'll let it condense, right? That's condensation, right? When gas changes to liquid, condensation, sublimation is going from liquid, from gaseous, from solid directly to gas. That's sublimation. Then desublimation, or whatever is it I called it, or deposition, that's the correct term, from gas to what? To solid. things that do that, CO2, we mentioned that, iodine, right? Good. So we said that this guy is going now. So at that gaseous state, C, or no, let's call it vapor, has high energy. Is that okay? So by the time it begins to condense, to need some energy to do what? To form bond. You know before, bond breakage here, right? Happen. So what will happen here? Bond formation. Is that okay? So when the bond has been formed, it becomes liquid, right? You now place it in freezer. What will happen? To begin to reduce again, right? Up to a point where it becomes to, okay, so we said that some of this energy will be required. Are you there? Some of the energy, so energy is still keep, so temperature against energy, is that okay? So energy keeps being added to the system. So as energy is still adding onto it, there's no change in temperature here, which means latency again, right? So which means that there is some energy is being used to form what? Bond again. Which bond now? A stronger bond, right? We know the bond in ice are stronger than those in water, right? And those in water are stronger than gas. So bond formation again, then before final, do you get it? There's going to be a reduction in temperature again. Is that clear? So that's what latent. So it's called fusion of ice here. Melting occurs in the opposite direction, but fusion of ice occurs. Do you understand now? So that's like fusion, and we refer it as